Welcome to this video on exam technique. In this video we're going to look at the EDEXCEL Unit 2 application of core principles of chemistry, and this was the June 2014 paper. So the whole point of going through these papers is to go through the answers to them and to make sure not only that you know the answers but you understand why them answers are the case as well. And along the way we're going to give you some little hints and tips as well to help you make sure that you get all the marks you can in the exam paper. As you can see on the left hand side, we've got some links, and the links click to different questions in the paper. So if you've got the hold of the paper yourself, you can have a go at the paper first, and then you can click back and have a look at the answers in this video. And if you want to skip to a certain question, then you can click any of the links on the left and it will take you to that section as well. The reason why these videos are actually quite important is because it's one thing being able to read the book and knowing the content. It's a completely different skill actually being able to answer an exam paper correctly. We call that exam technique. So this video aims to mainly go through that side and address that side of the course, which is the exam technique side. So let's get started. Okay, so section A in the EDEXCEL paper starts off with multi-choice questions. So all we have to do is put a cross at the box that says, when sodium is added to ethanol, which of the following observations would be made? So you might have seen this reaction before. It fizzes, so it effervesces. It certainly wouldn't have any colour change, and there certainly would be a reaction when you react it as well. So this one, it fizzes and it moves around in a ball. Okay, question 2. So question 2 says, which of the following substances does not have intermolecular hydrogen bonds? For hydrogen bonding you need a nitrogen, oxygen and fluorine, and there must be a hydrogen attached to that as well. So ethanoic acid does, it has the OH, methanol has OH, and obviously water has OH. The only one which doesn't is this. This is a carbonyl group, but it's a double bond O and it's not bonded to a hydrogen. So therefore this is not hydrogen bonding. So the answer is B. That has no hydrogen bonding, which is propanone. Okay, and part 3, question 3, says which of the following molecules has the lowest boiling temperature? You're looking for the molecule with the shortest hydrocarbon chain. You can see this one is 1, 2, 3, 4. This is butane. Pentane has 5. This one is propane. This is propene, sorry, because we've got 3 carbons there, and this one's got 1, 2, 3, 4, 5, 6. So the answer is C, because it's the least number of carbons. It's basically the smallest molecule, lowest MR. So that one's going to be C. Okay, right, on to the next part. So question 4. Let's drag that down there. Okay, so question 4 says, which of the following molecules is the highest melting temperature? So what we're looking for here is a molecule that can pack together very, very closely and have lots of van der Waals interactions. Anything with branches on is really going to not allow these molecules to pack together very, very closely. So A, B, and C are all out, and D is a nice linear molecule. You can pack loads of them together, lots of van der Waals forces along the chain. So therefore, it's D is going to have the highest melting temperature. Okay, and then question 5. So it says, which of the following isomeric alcohols with a molecular formula C5H12O can be oxidized to a carboxylic acid with 5 carbon atoms? Right, so we're looking for carboxylic acid to be formed, we need a primary alcohol, and that's what you're looking for. This one is a secondary alcohol because the OH is bonded to a carbon, which is then bonded to 2 other carbons. This is secondary as well. This one is actually tertiary because we've got an alcohol bonded to a carbon which is bonded to 3 other carbons. This one is primary because this is bonded to a carbon which is bonded to 1 other carbon. So this one is the only one which can oxidize to a carboxylic acid. So that's going to be D. Okay, right, on to the next part. Okay, so this is quite a big question, as you can see here. So this is question 6. It says, consider the infrared spectrum shown below. And they've given us the spectrum here. And they've also given us, as you can see, our absorption ranges for each of the different types. And basically the question is then asking, which of the following could have produced the above spectrum: an aldehyde, an alcohol, a carboxylic acid, and a ketone? Well, the biggest giveaway really here is we have this big broad peak, which is here. A broad peak around about the 3000 mark signifies an OH bond. So immediately we can remove aldehyde and ketone from the mix. And so then all we've got left is alcohol and carboxylic acid. Now, if we look at the data they've given us here, you can see that we've got an OH stretch here, carboxylic acids between 330 and 250, which does match that. If we look at the alcohol one, it'll be 3750 to 3200, which would mean this would be shifted a bit further up. So this OH is caused in a carboxylic acid. So the answer is C, which is the carboxylic acid. There we go. Okay, so on to question 7. Okay, so question 7 says, in a mass spectrum of butane, C4H10, where would a peak be seen for the molecular ion if it had a charge of 2+? Well, if it's a 1+ charge, then it would have just the molecular mass of this, which would be 58. But whenever you have a 2+ charge, because this is a mass to charge ratio, so mass to charge, or you might also see it as m/z. The m is the mass. Now we know the mass is 58. So if we put 58 on there, the charge is 2, because it's saying 2+, so we divide that by 2, and that should give us 29, and that should be our answer. So effectively it appears halfway up the spectrum. Okay. So the next question, number 8. When a flame test is carried out on calcium iodide, the colour of the flame is, so because it's a calcium based compound, that's what the flame test is testing for. Calcium is a yellowy red colour. So the answer is A. Okay, question 9. So it says the indicator methyl orange is a weak acid and may be represented by the formula HA. The equation for its dissociation is shown below. And you see we've got HA, A-, and H+, and we've got the colours as well. Under certain conditions at equilibrium, a solution of HA has a yellow colour on addition of a small volume of dilute sodium hydroxide. The colour of the solution would, now we need to pick from the option, so we're going to add sodium hydroxide to this. Hydroxide is OH-. So the OH- will actually react with the H+. Now if this reacts with the H+, effectively this goes down, it depletes, and equilibrium will shift to replace them. So in other words, equilibrium will shift to the right. So the colour will actually go yellow. Because it was already yellow to start with, then we say effectively there is no change in colour, because equilibrium is still keeping it yellow, pushing over to the right hand side. So that one's no change. Okay. Right, on to question 10. Let's put that down. So let's consider the following group 2 compounds, and we've got the group 2 hydroxides and group 2 sulfates. The solubility, now we've got to know about the solubility of these, and effectively as we go down the group, the solubility of hydroxides increases, and as we go down the group as well, the solubility of sulfates decreases. So we need to read these really carefully. So it says increases down the group for both hydroxides and sulfates, but that's not correct. Increases down the group for hydroxides, but it increases up the group for sulfates. So this one is true, because this is literally, you have to read it really carefully, because this is going up the group for sulfates and down the group for hydroxides. So make sure you're reading it really carefully. So that one is B. Okay, question 11. Question 11 says, which of the following is the correct equation for the decomposition of corresponding nitrate, of the corresponding nitrate? So this one, nitrates are normally pretty, they decompose pretty readily, especially the group 2 ones. Some of the group 1 nitrates are a little bit more difficult to decompose. The only one which decomposes readily is lithium nitrate, which is this one here. They always produce nitrates as well, nitrogen dioxide, sorry, which is this brown gas. These two are not producing that here. So it is between these two, and lithium is the only one which will decompose readily. And this one, sodium nitrate, really struggles to decompose in a Bunsen burner. So this one is the one that's actually going to decompose, which is A. Okay, so that's the lithium one. Okay, on to the next question. So question 12. And it says, what is the oxidation number of phosphorus in P4O6? So all we have to do is just go write P and O. Oxygen is -2 individually. We've got 6 of them, so that's going to be -12. The whole molecule is neutral, so that means phosphorus in total must be +12 to balance out that -12 on the other side. Now, because we've got 4 of them, we need to take that 12 and we need to divide it by 4 to work out what 1 phosphorus is, and that gives us 3. And so therefore our oxidation state of phosphorus is +3 as a result. Okay. Right, on to the next one. Question 13. Alright, okay, so it says for barium, the third ionization energy is higher than the second ionization energy because, so the reason for this is actually this third electron here that they're trying to remove must be closer to the nucleus. We've got this attractive force between the nucleus and the electron. So the answer for this one is actually going to be D, because we are removing it from closer to the nucleus. Okay. Okay, so question 14. So it says here the reaction, let's switch up a little bit. The reaction profile for an endothermic reaction is shown below. And it says which arrow represents the activation energy for the forward reaction. So forward reaction is reactants go into products. So the activation energy is the amount of energy required to effectively allow the reaction to occur. So we're going from here all the way up to the peak of this energy profile here. So the answer is A. And then the next question, it then says which arrow represents the activation energy for the backward reaction. So the backward reaction here is going from products back to reactants, and that's going to be B. So it's just the same, it's just going the other way. Okay, so that one's B. Right, on to the next one. Right, 15. It says consider the Maxwell-Boltzmann distribution of energies for a gas shown below. EA represents the activation energy, which is there. It's got number of particles with energy E and energy E at the bottom there. Okay, so what we have to do, it says the shaded area of the diagram indicates the total number of particles that. So we're looking at this bit here. Activation energy is the energy required for a reaction to occur, for successful collisions to occur. Anything beyond that means the particles have enough energy for them to collide successfully to allow a reaction to occur. Anything below that means they don't have enough energy, which is the vast majority of the particles at any one time. So what we need to say is this is B. There you go. Right, question 16. So it says which of the following is a pure form of carbon that has both hexagonal and pentagonal rings in its structure and can conduct electricity. Right, hexagonal and pentagonal is a classic sign of Buckminster fullerene. You might get this confused with graphite. Graphite doesn't have both of these rings. It only has one of them, which is the hexagonal for graphite. So Buckminster fullerene has both. So that's the big giveaway there, really. Well, it's not much of a giveaway, but if you know it, then you should be able to get the mark there. Okay, and then question 17. It says hydrogen H2 is not completely carbon neutral fuel. Which of the following is an incorrect reason for this? So we're looking for the incorrect one, and that's the most important thing here. So we need to look at all of these statements here, and we should find that some carbon dioxide is released in the transportation. That's correct. Carbon dioxide is made when the electricity is generated for the manufacture of H2. That's correct. A small amount of carbon dioxide is produced on the combustion of H2 fuel. That's incorrect. You don't produce any carbon dioxide when you combust hydrogen fuel. You only produce water. So the incorrect one is actually C. And then this one, carbon dioxide is released during the construction of the manufacturing plant, and obviously that would be the case as well in the construction vehicles. So, okay. On to the next question. So question 18. Alright, okay. So it says when steam is passed over heated magnesium, which of the following occurs? This is really important. We're using steam. Magnesium reacts in two different ways. When it reacts with steam, it produces magnesium oxide. When it reacts with cold water, it produces a hydroxide. So because it's steam, we're producing an oxide here. So this one is A. You've got to really watch out for that one because that's quite tricky. Okay, and then the last one for section A, it says which of the following will not affect the rate of reaction below. We've got calcium carbonate solid, HCl aqueous, calcium chloride, aqueous, water and carbon dioxide. Surface area definitely will. Concentration will. If you have a higher concentration of hydrochloric acid, that means it will react quicker. Pressure won't, because pressure affects gases. We don't have any gases as reactants here, so therefore this is going to have no effect. And temperature will as well, because they'll have more kinetic energy, which could lead to more successful collisions, which lead to a reaction. So pressure is the one that is not will not affect it, because we don't have any gases as a reactant. We've got solid and aqueous solution. So there we go, 20 marks for section A. On to the next one. Okay, so this is question 20, section B. So these are like your extended answer questions. So we're going to start with this one. It says brand X is unlike many conventional toilet cleaners in that it does not contain bleach, but instead contains hydrochloric acid. The label states that the toilet cleaner contains 9 grams of HCl per 100 centimeters cubed of the toilet cleaner. An industrial technician was given the task of checking the validity of this statement. Using 25 centimeter cube portions of the toilet cleaner, the technician carried out a titration using 2.50 moles per dm cubed sodium hydroxide solution and obtained the following results. And we've got our titration results here. So it says complete the table and calculate the mean titer by selecting the appropriate results. Okay, so what we have to do is work out the volume added. So this is pretty straightforward. It's 25 minus nothing, which is just going to be 25 centimeters cubed. This one is going to be 49.60 minus 25, which is going to give us 24.60. And then this one is going to be 24.5. 0 minus nothing is just 24.50. So put that there, 24.50. Alright, so it then says complete the table to calculate the mean titer by selecting the appropriate results. So what we're looking for, when they're saying appropriate results, we're looking for concordant results. So concordancy appears where you get two results that are within 0.1 centimeters cubed of each other, and that would be these two here. This one isn't concordant, so we just omit that one. So we're using these two numbers here. So that's going to be 24.60 plus 24.50. Now, really don't need a calculator for this one. What's halfway between them two is 24.55, and that would be your mean titer. Okay, there you go. Okay, so on to the next one. Then it says write the equation for the titration reaction. State symbols are not required. So this is just a very straightforward reaction. Sodium hydroxide is going to react with hydrochloric acid, HCl, and that's going to form sodium chloride, which is your salt, plus water. There we go. So nice and easy. And then the next question, it says calculate the number of moles of sodium hydroxide that reacted. All right then, so what we need to do is moles of NaOH, so I'll put that there, is going to be the concentration times by the volume. So the concentration we were told was 2.50 moles per dm cubed of sodium hydroxide. So we're going to stick that down there, 2.50, and we're going to multiply that by the volume. Now this is the mean titer that we used, which is this number here. So let me just nudge that down there. So the mean titer is 24.55. This is in centimeters cubed though, and to work out the moles, you need to convert this to decimeters cubed. Now you can either divide by 1,000 there, or what you can do is just put this on the end, times by 10 to the minus 3 on the end of that number, and that means divide by 1,000. It just makes the calculation a little bit easier. Right, okay, so let's bring in our calculator. Let's work this out. So we've got 2.50, we're going to multiply that by 24.55 times by 10 to the minus 3, and we should get 0.061375, or if I put that into standard form, that's going to be 6.13 0.75 times by 10 to the minus 2, but I can simplify that. We can just put it as 6.14. And this is the number of moles, so just put mole on the end there. Okay, so there's your 1 mark. Okay, on to the next part. Okay, so it says, hence state the number of moles of hydrochloric acid that reacted with the sodium hydroxide. Well, as we can see, the equation was a 1-to-1. We know the number of moles of that, and so therefore, because it's 1-to-1, it's the same number of moles. So that makes it nice and easy. So the number of moles is just 6.14 times by 10 to the minus 2 moles. So that's pretty straightforward. And then it says, part 5, it says calculate the mass of HCl present in 100 centimeters cubed of the toilet cleaner. Give your answer to 3 significant figures. Right, now this is really important because we're using 100 centimeters cubed, it's stating. When we did the titration, if I bring this back, the amount that we actually titrated, we used 25 centimeter cubed of the toilet cleaner. So the titration we've done is we worked out the number of moles for 25 centimeters cubed. The question is after 100 centimeters cubed. So what we must do is take the number of moles that worked out here and multiply that by 4 first. So we're going to put 6.14 times by 10 to the minus 2, multiply that by 4. And this allows us to work out the number of moles in 100 centimeters cubed. So 6.14 times by 10 to the minus 2 times that by 4. And that's going to get us 0.2456. Alright, there you go. So that's the number of moles in 100 centimeters cubed. And then we need to work out the mass. Once we work out the mass is number of moles times by the MR of HCl. So I'll put that on there. So that's just a mole calculation. So mass is the number of moles in 100 centimeters cubed, which is this. It's 0.2456. Multiply that by the MR of HCl. Now Cl is 35.5 plus hydrogen, which is 1. So that's 36.5. Obviously, you'll have a periodic table to work that one out. And then that should give you, let's bring our calculator back in. Okay, so we should have 0.2456, and we're going to multiply that by 36.5, and we should get 8.9644. I'm just going to round that up. I'll just round it, so 8.96 grams. Okay, it's 2 marks, so you get 1 mark for actually working out, for actually multiplying by 4, and then 1 mark obviously for this equation here. So that's where you get your 2 marks for that one. Okay, and then next one. So V part 1, it says using the technician's results, comment on the validity of the manufacturer's statement that the toilet cleaner contained 9 grams of HCl per 100 centimeters cubed, and justify your answer. Well, you can see here that actually from the titration we've got 8.96 grams. That's pretty close to 9 grams, and so therefore we would say that the statement is actually valid, and this is because 8.96 grams is pretty much very close to 9 grams. So yeah, it's not too bad. And then the next bit. Okay, so it says explain why titrations involving the use of a 2.5 moles per dm cubed sodium hydroxide solution would not be advisable in a school or college laboratory. Right, so the reason why this is quite strong, this actually, and it'd be too corrosive. That's pretty pretty high concentration. So yeah, normally what you'd use in schools would be about 1 mole per dm cubed. 2.5 mole is pretty strong. So yeah. All right. Okay. So the next question. Okay. So this is B. It says conventional toilet cleaners contain a bleaching agent, which is chloric acid, HOCl, is one such substance. Draw a dot cross diagram for chloric acid and show outer electrons only. Right. So what we're going to do is going to draw our oxygen in the middle. We know oxygen has 6 electrons, and it's going to bond with the chlorine. It's going to share an electron there, and chlorine's obviously going to have 7 electrons in its outer shell. Oxygen has got 6 electrons. 1, 2, 3, 4, 5, 6. And then hydrogen is going to bond there, and that would get you the mark. You could draw it as an ionic compound as well. So, for example, you could do something like this with your positive charge, and then you could put in your oxygen. So, look something like this, cross Cl. You could draw it as an ionic compound like that. Either one of them will really do, so you get the mark there. And then part C. Okay, it says the instructions for the use of brand X state that the toilet cleaner should not be used with bleaching agents. Complete the equation for the reaction between the hydrochloric acid in the toilet cleaner and the chloric acid in the bleaching agent. Give a reason why this reaction is to be avoided in accordance with the instructions for the use of the toilet cleaner. Right, so we've got HCl and HOCl. Now, when these two react, we're going to produce water as one of the products. So we've got the H and the H and the O. So this O and the H will actually produce water. And what's left is chlorine. So we'll put Cl2 there, plus water. Now, the observant of you will probably notice that we're producing this nasty stuff, which is chlorine gas. It's toxic. So you should not mix these two together for that reason. So I'm going to put that there. So chlorine is a toxic gas. All right. Okay. Okay, so it says another bleaching agent is sodium chlorate, 1, which is NaClO, which can be purchased as a solution. It can also be obtained by bubbling chlorine gas into sodium hydroxide solution. So part 1, it says give the oxidation numbers of the chlorine containing species in the equation below and classify the reaction as a result of your answer. Right, so the oxidation numbers basically for elements is 0. For sodium chloride, this is +1, so this is going to be -1 for chlorine. And then sodium chloride, which is this one here. Now oxygen in this case is -2, and the sodium is +1. So therefore the chlorine has got to be +1, which is quite unusual really. So that's +1 there. Now you can see here the type of reaction. We're going from chlorine. It's been reduced here and it's been oxidized here. So when something is simultaneously reduced and oxidized from the same element, we call that a disproportionation reaction. I'm trying to say that one quick. So disproportionation. Okay, so you obviously get 2 marks for that. You get 1 mark for your oxidation numbers and 1 mark for disproportionation. Okay. So, there we go. On to the last part. So it says state how the reaction conditions would need to be changed in order to produce sodium chlorate instead of sodium 5-chlorate instead of sodium chlorate. So one of the ways in which you can do this is by increasing the temperature. So you have a higher temperature, so we're going to put that in there. Higher temperature. Or what you can do is you can increase the concentration of sodium hydroxide, anything like that, and that would allow it to, basically you're just oxidizing it further. Right, okay, and then the last one is give the equation for the reaction between chlorine and sodium hydroxide solution that forms sodium chlorate 5 as one of the products. State symbols are not required. Right, so basically this is very similar to the equation that we'd seen on the previous page here. So if I drag this across, there's our page there. There's our equation. You can see here that producing water, sodium chlorate and NaCl. So all we're going to do is change this for sodium 5-chlorate instead. This is just sodium 1. So these two remain the same, so they're the same products. So we're just going to come back onto this equation here. So we're going to add Cl2 is going to react with sodium hydroxide as it's suggested, and we're going to form sodium ClO3. We're going to form sodium chloride, which is our salt, and we're going to form water. Okay, so this is chlorate 5, because this is -6 in total. That's +1. So this one must be +5. That's how we know it's that formula there. And then all we have to do is then balance this up. Now you can see here that we've got an imbalance of hydrogens here. And really to try and the best way is to try and get even numbers on each side. So if I put a 3 on this side and then a 6 on this side, this balances out our hydrogens, and then obviously to balance out our sodiums as well, we need 5. We'll stick the 5 on this side so as to not disturb the oxygens again. So we're going to put a 5 there, and then the chlorine is going to obviously add up to 6 because we've got 5 there and 1 there, so we need to have a 3 there to make sure that adds up all to 6. So you get 2 marks for that, 1 for the correct equation, and then 1 for the actual balancing and making sure that it's all balanced. So you get the 2 marks there. And there you go. In total, you've got yourself 16 marks for that one there. So on to the next question. Okay, so this is question 21. Question number 21 says, this is a question about halogenoalkanes or haloalkanes. Halogenoalkanes can react with hydroxide ions in different ways, depending on the conditions used. Using 1-chloro-1-fluoroethane, CH3CHClF, as an example of a halogenoalkane, the following reaction could occur in aqueous solution. So we've got this equation here. Suggests why it's unlikely that the fluorine atom in CH3CHClF would be substituted by the hydroxide ion. Okay, so what we need to say here is that effectively the CF bond is actually stronger than the COH bond, which is attempting to substitute it. So because it's a much stronger bond, it's more likely to, well, it's very difficult for it to break and do that substitution reaction. So we're just going to put that there. So the CF bond is stronger than COH bond. All right, okay. So on to the next one. So it says a student attempted to draw the reaction mechanism for the reaction in A part 1, but made a total of 3 errors. So identify these errors and state how they should be corrected. Okay, so we'll start with that first one then. You can see here straight away you've got this dipole here that's the wrong way around. So the first thing is we're going to put dipole. So but dipole is wrong way round, and what we should see is actually the C should be delta positive, and the Cl should be delta negative. So there's your first mistake. Another error as well is actually, if you look at this arrow here, this is pretty bad actually. So this arrow should be going from the oxygen to the delta positive carbon here. So we need to write that first. So we first of all will state what the error is. So the arrow goes from C to OH. That's the error. This should be the other way round. Okay. All right, so there's your second one. And then the last mistake is if you look at this here, you can see that you've got a C and a H and an O. This really should be the other way around. That's not right. That bond should be bonded to the oxygen with the hydrogen on the outside. So this should be flipped around. So let's write that down on there. So we're looking at the product, and the C, the error is this C is bonding to the hydrogen on the OH group, on the hydroxyl group. Okay, and what we should be saying is this should be bonding to oxygen on OH. Okay, so it's three marks for all that, so it's quite a bit. You get 1 mark for this, 1 mark for that, and 1 mark for that as well, so not too bad. Okay, right, on to the next part. Okay, right, so it says in hot alcoholic solution, a different reaction may occur between halogenoalkanes and hydroxide ions. Write the equation for the reaction between 1-chloro-1-fluoroethane, CH3CHClF, and hydroxide ions in alcoholic solution. Right, so this is an alcoholic solution. So we're going to write that equation there. So this is going to be CH3, CHClF. React that with the hydroxide ions. You could put sodium hydroxide there instead if you like. And this is going to produce your CH2 CHF because the chlorine has been cleaved, Cl minus, and then obviously you're going to produce water as well, which is H2O. Okay, so you get 2 marks for this, and so the 2 marks come in by saying 1 for actually drawing the correct product there, to get 1 mark for that, and then you get 1 mark for the rest of the equation. So write that in there. So because this is an alcoholic solution, the chlorine is broken off from the molecule, and water is formed, and a hydrogen is removed as well. So this is effectively an elimination reaction, and so we're removing the hydrogen from here. That's why it's CH2 to form the water and a chlorine. So that's what you get when you've got it dissolved in alcoholic solution. Okay, so that's the key thing. Right. So let's note that up there. Okay, so it says chloroethane can be produced in various ways as shown below. Identify by name or formula the reagent needed for each of these reactions. Right, so we're going from C2H6 to C2H5Cl. So when we're doing a monosubstitution of chlorine, we're going to use with hydrogen, so replacing the hydrogen with the chlorine. That's what's happening here. The reagent we use for this is chlorine, Cl2. Going from alcohol to a haloalkane, we're going to use, we could use a few things actually. We could use PCl5 or PCl3. You could use conc HCl. You could use sodium chloride, which is obviously your salt, and obviously have a concentrated sulfuric acid, H2SO4. So you could have a few things there to convert that from alcohol to your halo or halogenoalkane. Okay, and then going from an alkene, which is this here, C2H4, to a haloalkane, we'll have to add a hydrogen and a chlorine to it. So this one's going to be HCl, a hydrogen chloride. Okay, so not too bad. Okay, so part C. See part 1, it says chloroethane will react with alcoholic ammonia initially to produce ethylamine. Complete the equation for this reaction. Okay, so let's write ethylamine first, because that's the product that we're producing. So it's going to be CH3, CH2, NH2. There's ethylamine. And we're starting with chloroethane, so let's put that over there. They've literally told you what's going to react. So there's your haloalkane. And then obviously the only other product that's left, obviously you've got a chlorine there and the hydrogen from here because that's NH2. So hydrogen from here, these will react to form HCl. And so you get 1 mark for all of that. Okay, and the next part, it says name the type mechanism for the reaction occurring in C part 1. Well, what we have is the ammonia is acting as a nucleophile because it's going for the delta positive carbon if we have to draw a mechanism. And it is effectively substituting the chlorine for an NH2. So this is nucleophilic. Nucleophilic substitution. So this is your nucleophile, lone pair of electrons on that nitrogen, and it will go for that double positive carbon. 2 marks here, 1 mark for nucleophilic and 1 mark for substitution. So again, not too bad. Right, and the next bit. What feature of the ammonia molecule enables the reaction C part 1 to take place? We've just mentioned it. It has a lone pair of electrons. So there you go. That's that one there. Right, on to the next part. Okay, so this is IV. Right, so it says if aqueous ammonia was used in C part 1 instead of alcoholic ammonia, suggest the identity of the organic product that would be formed. Well, what you would get is ethanol that's being produced. So instead of your amine. And then part D, there you go, it says ethanol. And then part D, it says dichlorodifluoromethane CCl2F2 is also known as Freon 12, and its manufacture was banned in 1994 under the terms of the Montreal Protocol. So it says complete the equation for the initiation stage and suggest equations for 2 of the propagation stages and a termination stage for the mechanism of the reaction that this molecule might undergo with ozone. Right, so we've got our Halogenoalkane here, and the molecule that we're going to, or the bit that we're going to break, is the chlorine's going to drop off. It's got the weakest bond. So we're going to draw this, that's CClF2 dot, there's your radical, and we're going to react that with Cl dot. So all initiation stages uses UV, and this is going to form 2 radicals that are produced. Okay, so the propagation, first propagation is we take the product of the last step and bring this down, and this is going to be a reactant of the next step. Okay, so it's this radical here. You could use this one as well if you like, and you can do the same reaction, but we'll just pinch this one here. So this is going to be ozone, O3, and that's going to form ClO dot. It's a little bit like past the radical, so the oxygen has shifted onto here to form ClO dot, and then oxygen is left behind, O2. You could do the same with this molecule as well, so this could react with O3, and you'll form ClF2O dot plus O2, so you could do that one as well. And again, we take the radical from the product, bring it down here, and this is for the second propagation step. That's going to be ClO dot. That's going to react with more ozone, and that's going to form again Cl dot. The radical produced here must be a reactant in the first propagation step, so that's a check there. So it must be ClO dot, and then what's left is 2O2. So in total, you produce 3 molecules of oxygen and use 2 molecules of ozone, and this is the degradation of it. Termination step, there's loads of steps here. You can just pick any 2 radicals and just react them together. So you can have 2 chlorine radicals, and that will obviously form chlorine gas. You can produce, you can have CClF2 dot reacting with the chlorine radical, and that will form CCl2F2. You could also have another one where you have your ClO dot reacting with another ClO dot, and that will produce chlorine, because you've got chlorine gas plus oxygen. So anything like that will do. And you get 4 marks for this question, so it's not too bad. You get 1 for this, 1 for that, 1 for that, and 1 for any one of them termination products. You only need 1 of them. Okay, right. So on to the next section. It says explain why the effect of Freon 12 molecules on the ozone layer was such a serious issue that scientists recommended its use to be discontinued. Right, 2 marks. Now, anything to do with the depletion of the ozone layer, which is exactly what this is doing, it would actually lead to more UV coming into the atmosphere, and then we know that UV actually leads to skin cancer. So it's a big problem. So it's 2 marks. So I'm going to write our first mark here. So the ozone layer is depleted and has allowed more UV to enter. And then you need to also give the effect as well. And there's your effect. So it depletes it, and then that leads to the environmental effect, which is obviously the cause of skin cancer in animals. So we've got 1 mark for obviously this first bit and 1 mark for the second bit, which is looking at the effects of it. Okay, and the next part, which is this one here. So it says the Freon 12 CCl2F2 could also be described as a greenhouse gas. Explain what the term greenhouse gas means. Well, greenhouse gases are like a big thick layer in the atmosphere, and if you have a really thick layer, it prevents heat from escaping as the Earth tries to cool overnight. So it's 2 marks. So we're going to put on here, this prevents infrared radiation escaping from the surface of the Earth. So it is 2 marks. So the first mark is prevents infrared radiation. You can use heat as well, prevents heat from escaping. And then you need to say where it's coming from. It's coming from the surface of the Earth. So mainly at night, if there's a lot of cloud cover, you might have noticed this. If there's loads and loads of cloud cover, and in a winter, for example, then you are not going to get a frost, or very unlikely to get a frost, because the cloud acts as an insulating property. It's a greenhouse gas. Whereas if it's really clear night and there's no clouds in the sky on a winter night, you notice the temperature really drops because the heat can escape from the Earth's atmosphere. So you actually notice this actually with water, because water is a greenhouse gas as well. Okay, so that's your 2 marks. And then on to the last part of this question. It's quite a big question. It says Freon 12 and other similar molecules are not normally viewed as contributors to the greenhouse effect, and suggests why this is so. So we know it's a greenhouse gas, but why is it not counted? The main reason is because we don't have much of it in the atmosphere, thankfully, because they banned it obviously back in 1994. So we need to say that there's a low amount of them in the atmosphere, or low abundance. And that's just a 1 mark question. So there we go. There's that's the end of that question. 23 marks, so quite a big chunk of marks there. And this also ends section B, and we go on to the last section, which is section C. Okay, so this is section C. So this is the last section in the paper, and it says spontaneous combustion is often a subject of fantasy in movies, but does actually happen with some chemical compounds. One such compound is silane, SiH4, which is analogous to methane, CH4. Methane is the main gas that is used in school and college laboratories with Bunsen burners, but it requires a spark or lighted splint to ignite. Silane does not require any such ignition, and at room temperature is spontaneously flammable. This can make an interesting chemical demonstration. One method of making silane is by mixing together 2 solids, silicon dioxide and magnesium, with the magnesium being in excess. The 2 chemicals are thoroughly mixed together. The mixture is then heated to red heat and initially produces powdered silicon. This silicon then reacts further with the excess magnesium powder and forms magnesium silicide, which is Mg2Si. The 2 reactions which occur are shown in the equations below. So you've got SiO2 plus 2Mg will form 2MgO plus Si, and then the Si reacts with 2Mg to form Mg2Si. The magnesium silicide formed is then reacted with hydrochloric acid to form silane SiH4. Right. So the question is basically asking us, this is complete and balance the equation for this reaction. State symbols are not required. Right. So we've got MgS Mg2Si, and that's reacting with HCl. So we need to just write down what we are producing. Now it did say that we're going to produce the SiH4, so I'm going to stick that over there. Okay, because that's one of our products. Now what's left is obviously magnesium and chlorine, and that would form magnesium chloride. So it's MgCl2. Magnesium's in group 2, so you need 2 chlorines to react with that. And all we have to do is then just to balance it. You see we've got 2 magnesiums there, so we need 2 in front there. We've got 4 chlorines, so we need 4 HCl over on that side. And you get 2 marks for that. You get 1 for balancing. And then you get 1 for the equation, obviously. To put equation over there. Alright, so 2 marks, not too bad. Okay, and the next part. So it says bubbles of silane rise to the surface in the reaction mixture and spontaneously combust with oxygen in the air. Suggest the names of formula of the products of the reaction between silane and oxygen. Right, so we know that silane is SH4, and it said that it was analogous to methane. So if we take methane and combust that in air, we produce carbon dioxide and water. Because this is not methane, this is silicon SiH4, we're going to form silicon dioxide instead of carbon dioxide. So it's going to be SiO2, and we're just going to produce water as normal. So it's 2 products. It's just the same, except obviously we're using silicon. So you get 1 mark for that and 1 mark for that to get 2 marks. Okay. And the next question says predict the molecular shape of silane SiH4 and suggest the bond angle. Right. So pretty straightforward on this, I suppose, as far as bond angles are concerned. The number of bond pairs we have here is silicon's in group 4. All the electrons in silicon in the outer shell are involved in bonding. So the number of bond pairs is 4. The number of lone pairs is nothing. So this is going to be a tetrahedral shape. And the bond angle in all tetrahedral is 109.5 degrees. So again, 2 marks for that. 1 for saying tetrahedral and 1 for saying 109.5. Okay, so on to the next part. Not too bad so far. Right, so it says explain why the SiH bond is longer than the CH bond. Right, what we need to say here is, remember the covalent bond is an attraction between the nucleus of one atom and the outer electrons of another. Now, if the atom's bigger, you're obviously going to have a weaker bond. So silicon is bigger than carbon. As you see in the periodic table, it's just below it. So that's the first thing we need to say, really, is silicon atom is bigger. Or you can say larger. Larger is probably a better word, actually. Let's put larger. And the other point, really, we need to say is that we have a weaker attraction. So put that on there. So we say we've got a weaker attraction between outer electrons and nucleus. So there we are, 2 marks. So yeah, basically it's just examining your understanding of a covalent bond, really. Okay, so the bigger the atom, the weaker the bond's going to be for covalent wise. Okay, and then next one. So this is quite a big question. 4 marks for this one. Identify the intermolecular forces present in pure samples of both silane and methane. Explain why silane has a higher boiling temperature than methane, and why both are gases at room temperature. Right. The key thing here is that they have London forces or dispersion forces or van der Waals. They've got a few different names. So that's the thing we need to talk about first. So we need to say London forces, or you can call them dispersion forces, or van der Waals forces, or anything like that. So these dispersion forces, that's the name of the intermolecular force that's present. And we need to say why it's got a higher boiling point. So we need to say that silane has more electrons. So remember, the more electrons you have, the more London forces you've got. So that's the key decider. So it's a bigger atom. So Silane has more electrons, and so therefore, there's another point just to make it clear. So hence has a stronger, or you can say more London forces. And as a result, obviously, we need to say that obviously that makes it a lot stronger, but then it also asks why both are gases at room temperature. And yes, although Silane does have more London forces and there's a higher boiling temperature, London forces are really weak compared to other forces, so you don't need much energy to break them, and that's why they're gases. So we need to say that London forces are weak. So little energy is required to break them. There you go. So 4 marks for all of that. Let's look at where the marks are. I've tried to break it down into the 4 marks as best as I can. So you get 1 mark for talking about the types of forces. 1 mark for saying that Silane has more electrons and therefore we have stronger forces. And then the last mark then ticks off the last bit, which is why both of them are gases at room temperature, and that's because they have weak London forces, so not much energy is required to break them, and hence that makes them a gas. Okay. Right, on to the next bit. So it's define the term electronegativity. So electronegativity, this is just something you have to remember, is the ability of an atom to attract electrons towards itself in a covalent bond. So the 2 marks coming here is you need to mention or emphasize the ability of an atom to attract the electrons. So that gets the first mark. And the second mark is you must include this bit in a covalent bond. That's where electronegativity only occurs if there's a covalent bond there. If we don't have a covalent bond, we are not talking about electronegativity. So that is a really important point. Okay, right. And then on to the last page. So it says some Pauling electronegativity values are selected for 4 selected elements are given below. You see we've got the information there. It says use the values in the table above, compare the polarity of the bonds in a molecule of methane with that found in a molecule of silane. It says comment on the significance of any difference. Okay, so what we need to say is we need to work out obviously the differences first of all between methane and silane. So let's start with the first one. So we'll have a look at methane first. So methane's difference is, so the methane is carbon and hydrogen. You can see that difference is 0.4. And silane, silane is we've got silica, which is 1.8, and the hydrogen, so that's a difference of 0.3. So that's your first part, is mentioning this difference. And we then have to say, it says we've got to compare the polarity of the bonds in a molecule of methane with that of molecule of silane, and then comment on the significance of any difference. So what we need to say, the comment we need to say is that CH bonds in methane are more polar than the SiH bonds in silane. So there's the comment bit. So CH bonds in methane are more polar than SiH bonds in silane. Okay, so that's the most important thing, and then we need to comment on the significance as well of the difference. So actually, the difference is not really that significant. There's only a difference of 0.1 between them. So we need to say for the last point is that the difference is not that significant. And if you want, you can quote the difference as only 0.1 if you want to quote that. So you get 3 marks for that. So 1 mark for mentioning what the difference is in the first place. You get 1 mark for making some kind of comment on what that means, what them numbers mean. And then the 3rd mark is the significance, the comment on the significance as asked in the question. Okay, so on to the next one. Okay, so this is part 3. It says using the table in F part 2, choose an element which, when covalently bonded to hydrogen, forms a molecule containing bonds that are more polar than those in silane or methane. Give the formula of the hydride of your chosen element and state the electronegativity difference. Right, so we're looking for something that's more polar than obviously the methane. So that's what it's asking for, is silane or methane, actually, either of them. So really we're looking for a big electronegative difference. So we can have the nitrogen and hydrogen, so that could be something like ammonia, so we have NH3. We could have hydrogen and fluorine, that's a big difference, so put hydrofluoric or hydrogen fluoride, as is HCl, it's a difference of 0.9 there. So that you could have HCl. You could put in oxygen, hydrogen, water, H2O, anything like that. And the electronegativity values for this one is 0.9 for ammonia. For HF, it was 1.9, which is a massive difference. HCl is 2.1, so that's a difference of 0.9. And water is 3.5, 2.1, that's 1.4. So any one of them will do. So you get 1 mark for obviously picking your molecule, 1 mark for stating the electronegativity difference. Okay, and the last one, which is B, or IB should I say, explain why it's possible for the bonds within a polar molecule to be polar, but for the molecule itself to be non-polar. Give an example of such a molecule. Right, there's loads of examples here. Basically, if you've got a molecule that's got polar bonds, but it's a symmetrical molecule, then overall the molecule itself is not polar. So we're going to put that in there. So bond polarities, effectively, they cancel in symmetrical molecules. And examples of these could be anything like BF3, SF6, you could put CCl4, carbon dioxide is a very common one, so definitely put that down. And also, you could also say, obviously, the molecules that we've done just up there is methane. Although it doesn't have much of a polarity, but it does have some polarity. It's symmetrical, and so is SiH4 as well. So any of them really. You'd get 2 marks for this. So the marks come in by saying 1 mark for saying the bond polarities cancel in symmetrical molecules, and 1 mark for any of these molecules here because they're all symmetrical. But there we go, not too bad. 21 marks, and that is the paper finished. Bye bye.